Hi there, everyone, and welcome back to Math 107. So, we finished up talking about the content in Chapter 2 of the course on sets and counting. I know it feels sort of weird that we started in Chapter 2 and are going back to Chapter 1, but I think it makes for a smoother entry into the course. Anyway, what we've been doing so far in Chapter 2, it may have been a different look at mathematics, but it probably still felt like what you would have classically considered math. Because for most students, when I say the word math, the first thing that pops into people's head is numbers. Every now and again, I'll hear something about algebra, maybe shapes if they like geometry. Every now and again, somebody gets cheeky with me and says something like pain or suffering. Please don't do that to me, it hurts a bit. Anyway, numbers popped up a lot. We were adding numbers, subtracting numbers, counting, things that you would traditionally associate with numbers and number systems. So what we're going to be doing in chapter 1 is a little bit different, but to my mind, it's actually really what lies at the heart of mathematics and all of those arithmetic processes we've been using all our lives. It's really about logic and reasoning. So we're going to take a look in this first section of chapter 1 at two different types of reasoning. I'll fill in that blank in the moment. So the first one we're going to talk about, though, is what I call inductive reasoning. So when we're doing inductive reasoning, we're basically making observations using the data from those observations to try to draw some general type of conclusion. So you can sort of think of this as, taking specific and going to general. So it's sort of widening as you move, from, as you're saying, you're going from narrow to broad in this instance when you do inductive reasoning. As an example of this that doesn't seem terribly mathematical in nature, this is a totally not fictitious example I heard from students talking outside my office one day. So I'm not going to read this for you. You've got the text on the screen in front of you. We're just going to roll with it. So you see what's going on here. We have a person who's made an observation about somebody's employment, and then they're drawing a conclusion from it. Technically, thanks to the quirks of the English language, the conclusion came before the observation, but you get the idea. They used what's happening with Fred to draw a generalization about what's happening at Stuff Mart. So this is inductive reasoning. I wouldn't call it particularly strong inductive reasoning since we've only got this single example, but that's what's going on. Now, it might be slightly stronger inductive reasoning if you end up hearing the response. So somebody else ends up saying the same thing happened to a couple of other people. So now we've got three separate data points supporting the conclusion that, Stuff Mart isn't a great paying, employer, because now we've got more than just a single person. It might not just be an accident of one person really sharpened their resume or did something that got them, a substantial improvement in their employment prospects. So that is inductive reasoning. We made some observations, we drew a conclusion based on them. So a big part of what ends up happening and what happened there is, I think I might have already said, that we're noticing a pattern. We saw more than one person having the same thing happen. So yeah, inductive reasoning really is about pattern recognition. That's a lot of what mathematicians end up doing, is looking at, data sets or observations of some sort and then ending up trying to notice a pattern and predict something like what comes next. So the next few examples will feel a little more mathematical in nature because we're basically trying to guess what's coming next in a sequence of numbers. So here I've got some, I call them numerical sequences. I think the book refers to them as arithmetic progressions, potato, potato. Hopefully you can follow. So we're going to work through these and I'll fill in the blanks as we go. So this first guy says 3, 7, 11, 15. By the way, along the way, feel free to pause this and think about things. I've only got so many minutes of recording time that I can execute, so I'm probably just going to assume that you pause while you think about your answer. In this instance, it looks like each pair of numbers is separated by 4. So it seems reasonable to guess that we can add 4 to the last term there, 15, to get the next guy, 19. Add 4 again to get the next term, 23, and that is in fact what I had in mind. For this next sequence, it's not quite as clear because if you look, one, the terms are positive and negative, so it's not like we're constantly adding the same thing. But you may notice that if you ignore the minus signs, 2 is, you get 6 by tripling 2, you get 18 by tripling 6. So you can check tripling 18 gives you 54. And then we have this alternating plus minus thing. If you didn't want to talk about it in terms of tripling, you can suggest that we are multiplying by -3 each time. That would give us the same sign change. And that ends up giving us terms following this -54 of 162 and -486. This third sequence is a little bit different because, again, it follows that same sort of, they're not, always increasing. But you can kind of imagine what's happening. There's two different ways I can imagine someone looking at this. The way I see it most of the time is students they see the 4 and the 11, so we added 7. Well, then we have to subtract 3 to get to 8. Then we add 7 again to get to 15, subtract 3 to get down to 12, and then, the sequence, as you say, the process kind of continues, and we end up with, in this instance, you'd see 16, and then 20. As you say, you go to 16 when you subtract 3, and then you go up to 23 when you add 7. That's one way you can do it. Alternatively, what folks might end up doing is looking at what you might call alternating terms of the sequence, breaking it apart into two separate sequences. So you have 4, 8, 12. Those are constantly, increasing by 4, so 16 would come next. Then you have 11, 15, 19, adding 4 again, so we still end up with 16, 23 either way. And that was what I was expecting. The last sequence, sorry for spoiling things where I went ahead and gave you the next two numbers. It's still 19 and 23, but it's a little bit trickier to suss this out. So if you want to play around, pause for a moment. Okay. So you might try adding around and seeing if you get some sort of successive chains of numbers here, and that might end up resulting in different values. I wasn't actually looking at any terms of adding 1, then 2, or anything like that in this instance. If you follow along the trail of numbers, 2, 3, 5, 7, 11, 13, and 17 are all what we call prime numbers. You can only divide them cleanly by themselves in 1. So the next two prime numbers after 17 are, in fact, 19 and 23. So that's what we've got going on there. The next example I want to take a look at isn't quite numerical, but it is sort of a case of pattern recognition, trying to figure out what's going on here. So this sequence isn't numerical in nature. I just gave you letters. So we have S, M, T, W. And I want you to guess the next two letters that would occur in this sequence. Again, feel free to pause, think about it. You may notice there's not really a progression through the alphabet because we go backward to get from S to M and then forward to T. So, trying to work out how you're bouncing around through the alphabet might not work. But if you look at this, if you try to think about somewhere that you might have seen a sequence of letters like this, it turns out, yeah, those are the days of the week. We've got Sunday, Monday, Tuesday, Wednesday. So I was expecting to see Thursday and then Friday after that. So I guess if you wanted to put in an R for Thursday, I wouldn't have held it against you so long as you explained what you were doing, but that was what I was expecting. So hopefully this is making sense so far in terms of inductive reasoning and pattern recognition. Now, inductive reasoning is really useful, but it has a couple of problems built into it. Thinking back to our first example, it's really only as good as the data that you have on hand when you make whatever conclusion you've got. So the more data you're able to gather, the better off you are. Like, for instance, if you think back to those sequences, you'd have had a much harder time predicting what was going on if I'd only given you the first 2 or 3 terms instead of giving you, the full number I did, especially with that sequence of primes. Or if I gave you that sequence of letters where I only gave you S, M, and T, maybe it's not immediately as clear that it looks like days of the week. Possibly the broader issue that you end up running into is that inductive reasoning's conclusions aren't really ironclad. It doesn't really prove anything. There's always kind of this niggling doubt in the back of your mind that maybe the pattern doesn't hold up at some stage. I could have just been a jerk as the person who made the sequence and declared that one of those things, the next number was 100, because I'm the one coming up with the sequence, blah ha ha. That's not my style, but hopefully you get the idea. So as an example of this sort of, not being able to prove anything. So Suppose you were in a political science class or a history course, something like that. You hear a classmate claim, we've never had a president over the age of 75. President Trump, still not there. You start thinking back, Barack Obama was known for being a younger guy. You start rolling back through the list. You get to, as you see, you get to Bill Clinton, also young. You think a bit more, well, okay, yeah, the famous presidents, guys like George Washington, Abraham Lincoln, Thomas Jefferson, none of them 75 in office. You may notice there's kind of a problem here because I conveniently stopped right before Ronald Reagan. He was 68 when he was first inaugurated. He served 2 terms. That's 8 years. He was, in fact, 76 for a short period at the very end of his presidency. You can look through the rest of the list. He's actually the only one. But thanks to the fact that he was president while over the age of 75, this claim is now, invalid. So this is what we might call a counterexample, and inductive reasoning doesn't really give you a way to get around the problem with a counterexample, possibly lying beyond the scope of the observations you've made. So we'll talk more about how you can deal with that in a moment, but I did want to take a look at one more example real quick. So this is a web app that used to be floating around on the internet. Unfortunately, it's been taken down now, but I was able to salvage a picture from it to work through what we're doing here. So this is a thing called regifting Robin. So I'll walk you through the process, and then we'll take a look at what it ends up meaning for us. So the idea here is we pick a 2-digit number. So I'm going to pick 86. Feel free to write down whatever you like. So once you've got that number picked out, you're going to subtract the number's digits from the number itself. So where I picked 86, I would subtract away 8. I would also subtract away 6. So 86 minus 8 leaves me at 78. 78 minus 6 drops me at 72. So then I go look at number 72 in the chart, and that's the gift that regifting Robin would have handed to me. In this case, a happy face mug. So take a moment, work through your own calculation, and enjoy your happy face mug too. So that can be a little bit freaky when I do this in class and I've got 20-some students in the room and they all go, whoa, we all got a happy face mug. It's like really kind of jarring and people will try to figure out what's going on. So as it turns out, we can do a little inductive reasoning to work this out. So you've got your own numbers sitting there. That's fine. I'll pick out a couple more just at random. So if I had started with 13, I need to subtract 1 and 3. That would drop me at 9. You notice you see a happy face mug there. Say I had picked 42. 42 minus 4 minus 2 takes me to 36. Oh, look, happy face mug again. So if you actually look around at the pattern, all those numbers that I've called out so far, they're multiples of 9, right? So in terms of what's happening, it feels like somehow regifting Robin knows that no matter what, we end up on a multiple of 9. So in terms of addressing exactly why this is the case, we've done some inductive data gathering, but actually getting down to brass tacks as to why it's happening, you might want to try to use deductive reasoning. We'll talk a bit more about deductive reasoning in the next video, but as opposed to going from specific observations to general conclusions, now we're sort of drilling down. We start from some kind of general principle and then end up making a specific conclusion based on it. That's where we're going to be heading next time. So